In this video, I'm going to discuss a comment that I got about this video I made a few months ago. So this was the previous video in my playlist on the foundations of quantum mechanics. So it was the meaning of quantum mechanics, the Copenhagen interpretation. And so this reply here that I got by Carl Hinman 2522 is what I'm going to be discussing. And so I've copied this over onto a Word document here, and his or her, I actually don't know, probably his, I think their name is Carl. But anyway, their response here is in this dark blue, where my writing will be in this sort of dark red here. And so I'm going to go through this response because this commenter brings up some good points, and I've sort of I made some errors in my previous video, particularly about referring to Niels Bohr as a logical positivist. And so this commenter sort of took me to task on making that claim and sort of showed why I was wrong about it. And I will provide more sources that show why I was wrong about that. Although, to be fair to, I guess, myself, uh, Bohr did share a lot of views with the logical positivists, but there are two important differences. One is his principle of complementarity, which I will discuss here, and two is that he came to his views largely independent of his interactions with the logical positivists. And so it would be kind of wrong to say that he was a positivist in the sense of, being, I guess, influenced by the logical positivists in the way that he came to his views about the interpretations of quantum mechanics. And so the commenter starts here by saying that there are serious problems here in my video that I was just showing. What is the Copenhagen interpretation of quantum mechanics? The first is that positivism is a red herring. So he says the issue isn't to discuss only what can be verified. So verification is something that the positivists were very interested in. That their claim is essentially that that only things that can be verified, essentially through the human senses, are the only things that are really worth talking about scientifically, and that everything else is sort of metaphysical mumbo jumbo. And so the commenter says the issue isn't to discuss only what can be verified, but to stop asking questions that nature isn't ever going to answer. And so to me, this seems like a distinction without a difference, because to say that we need to stop asking questions that nature isn't ever going to answer is essentially saying to stop asking questions that we can't verify. But, I think if we wanted to get into the semantics of it, we could say that there is a difference here. And so I'll grant this criticism here, that this is a criticism uh, uh, levied by this commenter here. And so the commenter says, you say in quantum mechanics the act of measurement has unavoidable and enormous consequences on the system. This does not necessarily make things non-classical, let alone categorically non-classical. So the commenter says there are plenty of classical measurements with unavoidable and enormous consequences. However, these consequences can be taken into account and compensated for precisely because such accounting does not invalidate the distinction between the system and experimental arrangement. In quantum physics, this distinction is empty. And so, again, I feel like there's somewhat of a distinction without a difference here, in saying that, if we can't make this compensation, if we can't take this into account and compensate for it, then these unavoidable and enormous consequences on the system are sort of making it categorically non-classical. If, we want to, I guess, define classical as the places where these consequences can be taken into account and compensated for. But again, I think the commenter's criticism here is valid, and I think maybe uh, if I want to be, I guess, as charitable to myself as possible, then maybe I could say that the way I worded it is kind of unclear. But I think the commenter's criticism here is valid, and so I will grant that the way that I said this, or even maybe the way that I conceptualized it, was incorrect or incomplete, and so I think this is important, and this will get into this idea of complementarity in Bohr's view of sort of, I guess, the epistemology of quantum mechanics, but. The commenter here, I just added these pictures here. So this is Niels Bohr, just so that this wasn't completely just full of, words here on your screen. But anyway, the commenter continues on. So after saying that the consequences in classical physics can be taken into account and compensated for, precisely because such accounting does not invalidate the distinction between the system and experimental arrangement. In quantum physics, that distinction is empty. Why? Because in quantum physics, the phenomena belong to what Bohr called the whole experimental arrangement, not to the system. And so again, that's Niels Bohr. And so what the commenter here is talking about, so a lot of times in science, and I'm a chemist, and so a big thing that we always make a distinction between is sort of the system that we're interested in and the surroundings. And you could, this is all throughout science, but you know in chemistry, the system is always sort of like the reaction that you're looking at, for instance. Then the surroundings would be, the solvent that it's in and the container that it's in. So if you want to look at like the heat of the reaction, you're interested in the heat of the reaction for the system, but you have to measure the surroundings. So like the solvents such as water and the calorimeter and things like that. And so we make this distinction between the system and the surroundings. And so what the commenter here is saying is that with Bohr, that when we're looking at quantum phenomena, that we can't really make that distinction of the system and the surroundings, where our experimental apparatus or measuring device would be part of the surroundings. That the measuring device is actually part of the system, and so it's the measuring device, and the way that we're measuring things is part of the system that we're measuring. So it's kind of that idea that when we're measuring a quantum system, we're not just measuring the system in isolation, we're measuring the system that is being measured in a particular way. And so down here, this gets into this idea of complementarity. And so I'll put two quotes here from this paper here, and I'll have these linked to in the lecture notes, which will be linked to in the description down below. So there's this paper here, and then I'm also going to quote here from the complementarity Wikipedia page. So from this paper here on the complementarity principle of Bohr. So the essence of the principle of complementarity of Bohr in physics is as follows. In any experience with micro-objects, so quantum systems, the observer receives information not about the properties of the objects in themselves, but about the properties of objects in connection with a particular situation, including in particular measuring instruments. And so again, that's that idea that I was talking about above, that when we're measuring the quantum system, we're not just measuring the system in isolation, we're measuring the system in the way that it interacts with our measuring instruments. So the measuring instruments are part of the system that we are actually trying to measure. So information about the object obtained under certain specific conditions should be considered as additional to the information obtained under other conditions. And so when we measure in one particular sort of measuring apparatus and experimental condition, and then we measure in a second apparatus and experimental condition, we will get these different results. And so these results have to be considered additional to each other. They're not sort of measuring the same thing just under different conditions. These are, two essentially different measurements that are occurring here. And so these should be considered as additional to the information obtained under other conditions. So experiment 1 is additional to experiment 2 with the two different experimental conditions. So, moreover, the information obtained under different conditions cannot be simply added, summed, combined into a kind of unified picture. So they reflect different or complementary sides of a single reality corresponding to the object under study. So the principle of complementarity finds this direct expression in particular in the idea of wave-particle duality and in uncertainty relations. So the need to describe the properties of quantum objects in the classical language of measuring devices leads to many paradoxes. So according to the complementarity principle formulated by Bohr in 1927, the solution of these paradoxes lies in the additionality of the classical description and quantum properties of micro-objects. So depending on the measurement conditions, the electron acts either as a wave or as a particle. So the definition of the particle trajectory masks its wave properties. Interference experiences leaves a trajectory uncertain. The classical description of wave properties are complementary. And the Wikipedia article here says that Bohr considered one of the foundational truths of quantum mechanics to be the fact that setting up an experiment to measure one quantity of a pair, for instance, the position of an electron, excludes the possibility of measuring the other, yet understanding both experiments is necessary to characterize the object under study. In Bohr's view, the behavior of atomic and subatomic objects cannot be separated from the measuring instruments that create the context in which the measured objects behave. Consequently, there is no single picture that unifies the results obtained in these different experimental contexts, and only the totality of the phenomena together can provide a completely informative description. And so what this is saying, in other words, let's say that we're running two different experiments that we'll call experiment 1 and experiment 2. Then the results obtained from experiment 1 are not just reflective of the quantum system that we want to interrogate, but the quantum system plus experimental apparatus and plus persons observing or analyzing the results. And if experiment 1 has a different apparatus and or observer than experiment 2, then the two experiments are interrogating complementary properties of the world. And so this can be seen, for instance, when we perform the double slit experiment with two different experimental setups. So there's one where we have no detector in front of the slits, and the other when we have a detector in front of one of the slits, or both of them. And so this is the double slit experiment here. So this is kind of what I'm going to be trying to portray in my illustration here. And so in the first one here, we have no detector, and so we get this interference pattern where we will have the electrons or photons or whatever going through these two slits showing up in these bands here where we have spaces in between where we are getting the destructive interference of the particle interacting with itself, or at least that's kind of the interpretation that we go with. And so it's creating this interference pattern. Whereas if we put a detector here, which is going to tell us which way that the particle moves through here, so through one slit or the other, we then lose our interference pattern here, and we'll actually just get a single blob right here. And so we will get, so the particle is sort of no longer interacting with itself if we want to use that interpretation of what is going on here. And so we lose this interference pattern. And so in the first experiment, we're observing the wave aspect of the electron, while in the second we're observing the particle aspect of the electron. So these complementary properties of the electron are observed because we're using different experimental apparatuses. So the one here where we don't have this detector, and the one here where we do have this detector. And so these experimental apparatuses are themselves an integral part of the system being interrogated. And so we can't say that, in both of these experiments, we are measuring sort of the same quantum system. So say we're putting an electron through these slits here, we wouldn't be able to say that, in the first experiment we are, looking at an electron, and then in the second experiment we're looking at an electron. We would have to say in the first experiment we're looking at an electron where we are not measuring the electron before it goes through the slits. Then in the second one we are measuring an electron before it goes through the slits. And so making that distinction there of whether we're measuring it going through the slits or not is part of the system that we are actually measuring. And the complementary properties that we're looking at here, and the first one is we're looking at the wave property of our electron, where in the second one we are looking at the particle property of the electron. And so that's why in the first one we get the interference pattern, where in the second one we do not get the interference pattern. And so these complementary observables can be seen in the commutation relations here. So the first one is the position and momentum. The second one is the energy and time. And then these last three here are the spins of our objects. And so we are getting these, we are sort of observing these complementary things when we use these different experimental setups. And so the commenter goes on to say, sort of summing up what they were saying before and what I've kind of been talking about here, is they say another more succinct way of putting this to say that measurements are the physical world, full stop. This is one reason why the idea of quantum measurement problem is utterly alien to Bohr's whole line of thought. And so I put this comment here to kind of back this up. So this is from this, well, I think this is the Stanford Encyclopedia entry of philosophy entry on the measurement in quantum theory. And so it says the issue of whether measurements or measurement was also a necessary condition for the assignment of values to physical quantities remained a question of controversy within the Copenhagen school. Bohr seems not to have insisted on this. Heisenberg, by contrast, at least in his early positivistic writings, seems committed to strengthening P, which was a proposition that the author refers to here. So that's the proposition endorsed by Bohr. If a quantity Q is measured in system S at time t, then Q has a particular value in S at t. So that measurement is both necessary and sufficient for assignment of a determinate value to a physical quantity. And so the commenter goes on to say, as to Kant, the relation between Bohr and Kant is non-trivial, but I agree with Ulrich Morhoff, who wrote, and so the commenter here is quoting this person right here. And so while QB is, so that's quantum Bayesianness, and I'm actually going to talk a bit about quantum Bayesianism in the next video after this one, but it's essentially a sort of subjectivist view of quantum mechanics. But while quantum Bayesianists deserve credit for their spirited defense of this position, the definiteness and irreversibility of quantum measurements, Niels Bohr urged it nearly a century ago, albeit in such elliptic ways that the core of his message has been lost or distorted beyond recognition. Then as now, the objectivity of empirical science was called into question. It was defended by Bohr along the lines of Kant's then revolutionary theory of science, according to which the possibility of empirical science hinges on the possibility of thinking of experiences as experiences of a system of interacting, re-identifiable objects. What Bohr added to Kant's theory was his insight that empirical knowledge was not necessarily limited to what is directly accessible to the senses, and that therefore it does not have to be solely a knowledge of objects of sensible intuition. It can also be a knowledge of phenomena that are not objects of sensible intuition, but instead are constituted by experimental contexts, which are objects of sensible intuition. And so the commenter then says, of course, to adopt this view of Bohr is to stop viewing him as a logical positivist. And so the logical positivists, as I discussed earlier in this video and in the last video, were really interested in this idea of knowledge being only things that you can verify using your human senses. And so what this quote here by my commenter is saying is that what Bohr added to Kant's theory was his insight that empirical knowledge was not necessarily limited to what is directly accessible to the senses, and that therefore it does not have to be solely a knowledge of objects of sensible intuition. It can also be a knowledge of phenomena that are not objects of sensible intuition, but instead are constituted by experimental contexts, which are objects of sensible intuition. And so it's essentially saying that we have these experimental apparatuses that can, probe our systems in some way that, doesn't have like a good analog to our sort of human senses. But then we can get readouts from our experimental apparatuses that do sort of translate this phenomena into something that can be experienced by the senses. But the actual sort of probe of our experimental apparatus isn't something that we could say has like a good analog of our human senses. And so we are sort of probing things that are not directly accessible to our senses, even though we are sort of translating it into, I guess, a readout or observation of the experimental apparatus that is observable using the human senses. So I put here a picture of Rudolf Carnap because he was kind of, I guess, the one of the big voices, one of the big figureheads in the logical positivist movement. And so, like the paper that I'm talking about here, or that I'm quoting from here, is actually called "What Bohr Wanted Carnap to Learn from Quantum Mechanics." And so, this paper here is sort of making the argument, well, it's making sort of two arguments essentially. The first one is that Bohr did actually, at least like in the 30s, the 1930s, have a little bit more interaction with the logical positivists than what some people argue. But the other thing that this paper argues is that the influence between Bohr and the logical positivists actually sort of went in the direction of Bohr being more influential on the logical positivists than that the logical positivists were influencing Bohr's thinking. And so the quote here from this paper is that sometimes philosophers have accused Bohr's interpretation of quantum mechanics for being positivistic. And so that's kind of the thing that I accused Bohr of being in my previous video that the commenter here has sort of taken me to task about. And so this paper sort of backs up what that commenter was saying that I got wrong, in that Bohr was not a logical positivist, which is sort of what I alleged in my previous video and what I was wrong about that the commenter has pointed out. So yeah, this paper says sometimes philosophers have accused Bohr's interpretation of quantum mechanics for being positivistic, but except for his attempt to express himself less metaphysically after criticism by some of the logical positivists, little supports such an allegation. Bohr had arrived at his interpretation years before his personal encounter with Rudolf Carnap and Otto Neurath. And sorry if I'm mispronouncing that. I've only seen the word written. And before his correspondence with the latter, so with Otto Neurath here. So Bohr based, for the most part, his interpretation on physical considerations and not philosophical principles. It is true that Bohr very early on was in touch with Danish philosopher, and again, sorry for mispronouncing things. So Harald Hofding or Hafding, I think that's how you pronounce that letter or something like that. But anyway, who considered himself an empiricist and classical positivist. Through him, Bohr had received a general introduction into philosophy, which indeed was part of the philosophical presuppositions behind his approach into understanding quantum theory. But apart from this guy's early inspiration, Bohr was not influenced by contemporary philosophy. And what the paper means by contemporary philosophy is the logical positivist school. In fact, Bohr believed that much influence between physics and philosophy went the other direction, such that philosophy learned from physics. And so, indeed, as I'll show in other quotes below, Bohr really wanted the logical positivists to take on his complementarity principle. So it seemed, well, we'll get into that here in a little bit. So my commenter here continues on. So as to quotes from Bohr, I would add one more to my mind, the key idea. So any attempt to track down further the course of events entails a modification of the experimental apparatus incompatible with the manifestation of the original phenomenon. And so essentially what it's saying is that if we want to track down further sort of the thing that we are looking at, we have to change our experimental apparatus. But if we're changing the experimental apparatus, then we're changing the system that we are actually experimenting on. And so we are actually changing the, the new results from this new experimental apparatus will be incompatible with the original phenomenon from our sort of first experiment. And so again, if we're looking at the double slit experiment, so up here, so we do this experiment, we get this diffraction pattern here, and then we put this detector here because we want to sort of look at this phenomenon in a different way. Essentially, we are now looking at a new phenomenon, and so this is changing the manifestation here of it. So our new result with that detector there is incompatible with the manifestation of the original phenomenon. And so it's incompatible with that diffraction pattern that we saw in the first experiment. And so we are, like I have been kind of drilling home in this video, we're experimenting on a new system, the system containing the experimental apparatus itself, including putting that other detector there. And so the commenter goes on to say, this is why Bohr thought it pointless to describe what happens between measurements, since any such attempt at further delineation would invalidate the phenomenon, i.e. preparation and outcome, long before any between became visible. And so I will close out here with a few more quotes that will sort of back up what this commenter has been saying I was wrong about here. So this is from this paper, What Bohr Wanted Carnap to Learn from Quantum Mechanics. So one of the most important tenets of the unity of science movement within the logical positivism. So the unity of science movement was a movement in logical positivism that wanted to say that we could sort of unify science together in order to because we all of the observations are done by the human senses, and so we could unify the science together sort of using that. So one of the most important tenets of the unity of science movement within logical positivism was the claim that all scientific statements, in order to be meaningful, should be related to objectively describable, directly observable states of affairs. Likewise, the movement insisted on the existence of some unitary observational and methodological principles from which all scientific knowledge could be established. So when Bohr got a chance to engage with the unity of science movement, as we shall see, he nurtured a desire to persuade them to see complementarity as the general epistemological lesson for all of science, that an objective description of nature is not separable from the observational and experimental conditions under which we explore nature. And then, so this next quote is from the same paper. In fact, all three of these are from the same paper. So, based on his interpretation of quantum theory, Bohr argued that the unified causal space-time description of classical physics had to be replaced by complementary descriptions in quantum mechanics in order to preserve objectivity. In quantum theory, we must use the same concepts as in classical mechanics, but the meaningful application of these concepts to atomic objects is tied to the experimental and observational situation, which excludes that those concepts, which normally apply simultaneously in classical physics, also did so in quantum mechanics. And so these complementary things, like wave and particle, where these things do not apply simultaneously in quantum mechanics. So things that might apply simultaneously in classical physics, like say the position and momentum of an object, cannot apply simultaneously in quantum mechanics. These are these complementary properties that Bohr was interested in. And so in quantum theory, we must use the same concepts as in classical mechanics, but the meaningful application of these concepts to atomic objects is tied to the experimental and observational situation, which excludes that those concepts, which normally apply simultaneously in classical physics, also did so in quantum mechanics. It was Bohr's firm belief that this lesson could be extended to other areas of human knowledge as well. In fact, this paper talks a bit about how Bohr wanted to try to, get this complementarity idea into even places like biology and things like that. So this last quote here from this paper, so in our opinion, something speaks in favor of Carnap's impression that Bohr basically agreed with the positivists with respect to epistemology and the importance of observational language. Nonetheless, Bohr might have felt that they did not understand the importance of the physical conditions of using complementary descriptions. So Bohr might therefore have expected that since he and the positivists mutually shared some basic ideas about observation, then the positivists might eventually become advocates of complementarity if they worked more closely with the observational problems connected to it. After several visits to Copenhagen in 1934, also Neurath saw similarities between Bohr's views and those of the logical positivists. About his encounters with Bohr, Neurath writes to Carnap that he obviously tries to come into agreement with us. This is seen from Neurath's perspective, but from Bohr's perspective, as we argue here, so the authors say that as we argue in this paper, such an agreement would also consist of the positivist acceptance of complementarity. And so what the authors of this paper are saying is that while there is a lot of overlap between Bohr and the positivists, especially in wanting to really drill down on the fact that we have to use observations, that we can't really meaningfully talk about phenomena that are not observed or not observable, that there was this difference, and the primary difference was this idea of complementarity. So that the different experimental setups are going to get these different results because the experimental setup is an integral part of the actual system that we are experimenting on, and that we are then looking at complementary sort of properties of the system when we are using these different experimental setups. So one other thing, so Agential Realism by Karen Barad here. So Karen Barad was somebody who is very interested in Bohr's sort of complementarity in his view of the Copenhagen interpretation. So agential realism sort of takes the Copenhagen interpretation and the complementarity, and especially the idea that the experimental apparatus is an integral part of the actual system that we are experimenting on. And so in an agential realist sense, the smallest units of analysis are phenomena. So a phenomenon is a specific intra-action of an object and the measuring agencies the object and the measuring agencies emerge from, rather than precede the interaction and produces them. And so this is the idea that we are producing the thing that we are observing by actually performing the experiment. And so the experimental apparatus is the integral part of the system that we are experimenting on. So by performing the experiment, we are actually producing the thing that we are observing. So the central idea is that the thing we research is enacted in entanglement with the way we research it. So the way being sort of the experimental apparatus, the thing being sort of the thing that we are probing, and then we being sort of the observers here. So this is an onto-epistemological offset, meaning onto as an ontology and epistemology as in knowledge. And so practices of knowing and being are not isolable. So again, that idea that when we are probing our system, our experimental apparatus is actually part of the system. We're not isolating sort of, the quantum system, quote unquote, that we are actually measuring sort of the quote unquote quantum system as part of the measuring apparatus, which is also part of the system. So the system and the apparatus are all part of the system. They are mutually implicated. We don't obtain knowledge by standing outside the world. We know because we are of the world. We are part of the world in its differential becoming. The separation of epistemology from ontology is a reverberation of a metaphysics that assumes an inherent difference between human and non-human, subject and object, mind and body, matter and discourse. And so Karen Barad was part of like the feminist epistemology, and so Karen Barad was sort of trying to take this idea of the experimental apparatus being part of the system being measured, sort of producing the measurement that we are getting, and trying to bring this into this idea that that there is no like objectivity in science. So I'm not going to go too much into this. I will have some links in the lecture notes here that if you want to look at those, if you want to look at Karen Barad's work on this, if that's something you're interested in, then you can check those out. But anyway, these are the references here. But anyway, that was what I wanted to talk about in this video. So probably the main take-home message, apart from me being wrong about calling Bohr a logical positivist, is this idea of complementarity principle of Bohr here. And so that is kind of a huge part of Bohr's thinking on the interpretation of quantum mechanics and the Copenhagen interpretation in particular. But anyway, I hope you found this video helpful, and I will see you in the next one.